Okay, so we're nearing the end of the semester, although we've got a few weeks left still. We're going to finish up sequences and series this week. I think probably on Tuesday, which will also be when I post or give out the take-home test. After that, it's sort of weirdly structured. After that, we have polar and parametric coordinates. So just a week or whatever each at the very end of the semester. It feels like kind of an anti-climax, but they are important. So today we're going to look at two applications, I guess you'd say, of the Taylor series. The second one is really critical. This first one, a little less so, but it's kind of cute. So the binomial theorem is a theorem that gives the expansion of 1 plus x to the n. And you can generalize it. So instead of a 1, you have an a, but fundamentally, this is what the binomial theorem says. Skipping the really important parts, they're skipping the components, the coefficients. This is a statement of the binomial theorem, and this notation, you by now might have taken some kind of probability course and seen this before. This is M choose K. It's called that because if we have a group of, say, 5 items, and we want to choose 3 of them, and it doesn't matter which order we do that in, then there are 5 choose 3 ways of doing that. So that's where that terminology comes from. But for our purposes, we're not looking at permutations or combinations or anything like that. We'll think of M choose K just in terms of a formula. It's m factorial over k factorial times m minus k factorial. And the binomial theorem, as it's presented here, requires m to be a positive integer. And the reason it requires m to be a positive integer is that we're taking the factorial of m, and we can only take the factorial of positive integers. And the first thing we're going to do as sort of an application of the Taylor series is generalize this to work for any value of m. And let's see where these binomial coefficients come from. Well, there are multiple ways of getting these. Like you might have seen, there's like a picture you can draw of a triangle, and the coefficients are entries in the triangle. You don't, strictly speaking, need calculus for this, but the binomial coefficients, these m choose k values, can be gotten from calculus using the Taylor series. We say, okay, we've got this is a function. We can take its Taylor series and try to write it as a sum. And so far, and in general, all of our Taylor series have been infinite. What will happen here if we hit this with the Taylor series is that past a certain point, all of our terms are going to be zero. So the infinite Taylor series will turn into a finite sum. Let me. So the first term of the Taylor series comes before you take any derivatives. Once again, I'm being a little sloppy with my language here. We're taking specifically the Maclaurin series. We're taking the Taylor series centered around 0. So f of 0 is 1 to the m power, which is always 1. Then f prime of x is m times 1 plus x to the m minus 1, and we plug 0 in for here, and we get m. And a factorial like pattern is going to emerge pretty quickly. So every time we plug 0 into these things, we're going to have 1 plus 0 raised to a power. So this is always going to be 1. And it's the numbers in front of the power that are going to survive when we stick 0 in. We'll see that again when we take the second derivative. Now we've got an m and we've got an m minus 1. But again, sticking 0 in here, we've got the m, we've got the m minus 1. This goes away. It's 1 to the power of m minus 2. 1 to a power is 1. Multiplying by 1 doesn't do anything. Similarly, f triple prime of 0 is going to be m minus 1, m minus 2. This does not go on forever, though. This is a finite process. Because eventually, you see, every time we take a derivative, this m gets reduced by 1. Eventually, we're going to take a derivative, and we'll get a bunch of constants out front. And we'll get 1 plus x raised to the 0 power, and anything raised to the 0 power is 1. So we're multiplying by 1. That's not doing anything. And this derivative is a constant. And when we take the next derivative, well, the derivative of a constant is 0. And when we take the next derivative, well, the derivative of a constant is 0. So after a finite number of derivatives, we start getting 0. And what we're finding here, these are the derivatives at 0. So this isn't any kind of final answer. This is, maybe I should have made this more explicit to begin with, but we're trying to find the Taylor series. So we do need these derivatives at 0, but we also need derivatives in there. And we're going to be multiplying these by powers of x. And when we add these together, we get the Taylor series. And again, the Taylor series is in general infinite. But here, our terms become 0. So there are only finitely many non-zero terms. And we wind up then A sub k is the Taylor coefficient. It's the things in front of the powers. We find that A sub k is m minus 1 to m minus k plus 1 all divided by k factorial. Let's talk about this a little. In particular, let's make sure we're all on the same page about that plus 1. You see, when we're finding A sub 2, when we're taking the second derivative, we get to a minus 1. When we're finding A sub 3, when we're taking the third derivative, we get to a minus 2. So in general, we wind up at can't use m, we're using m for something else. We don't quite reach the derivative we're taking. If we're taking the nth derivative, we get to minus n plus 1. And this is the binomial coefficient. This is m choose k. It's not written as m choose k. But it is. And in particular, what's going on here to make this look like m choose k is we can keep this pattern going. We'll put the next term. We're going negative minus 1, minus 2, minus 3, and so forth. We keep counting down. And we put that term in both the numerator and the denominator. So this isn't changing the expression because these two terms cancel each other out. And then we put the next term up here. and the next term down here. And we just keep counting down. And now we have in the top, we have m factorial. So we start at m and we count all the way down to 1. In the bottom, we have this k factorial. And then we have all of these terms. M minus k factorial. So there's the binomial coefficient. There's m choose k. And the reason we do this is just, partly it makes it a lot easier to remember. Partly it's because if you're trying to do stuff on your calculator will have a factorial button. So it's nice to have factorials. Whereas, if we wanted to take just this and plug it into our calculator, we'd have to do that by hand, type in 17 times 16 times 15, that would be annoying. So there are good reasons to do this, but we have lost something here because again, if we're taking m factorial, m has to be a positive integer. If I now erase all of this and get us back to what we had originally, there's nothing here that requires m to be a positive integer. I mean, m could be 1/2 and k could be 7, and everything we have written on the board is perfectly defined. And this, in general, 1 plus x to the power of m is 1 plus, and now I won't use this m choose k notation because this m choose, well, I'll still use the m choose k notation, but I'll make it explicit that we're not defining m choose k in terms of factorials. M choose k is m times m minus 1 times m minus 2. Down to m minus k plus 1. In the bottom, we have a k factorial. In case you were wondering, that's never going to be an issue because k is our index. We start at 1 and then count up 2, 3, 4, 5, 6 until we reach m plus 1. So the k factorial is not causing us trouble. There's no chance of k being a fraction or negative or anything like that. And if m is not a positive integer, then we can keep going forever. This no longer terminates, and it becomes an infinite Taylor series. But it's still perfectly true that 1 plus x to the m equals this sum. It's just that this sum is now infinite. well, we don't terminate, so we want to keep going forever there. Again, when we have, if m is finite, these terms become 0. So, you know, the square root of 1 plus x. This is a power. It's 1 plus x to the 1/2 power. And we can write this as an infinite series. We need, again, we're going to let 0 be our center here. We're taking the Maclaurin series. So we should start with the first term, and that's 1, right? When we find the first term of the series, we're just using the function. We stick 0 in here. 1 plus 0 is 1. The square root of 1 is 1. A sub 1 is 1/2. Then our terms from here on out, 1/2 choose 2 is perfectly well defined the way we've defined n choose k. Again, so we end at a -1. That's less than 2. It's 1 less than 2. 1/2 choose 3. It's going to be this thing. It's no longer a factorial, but it has a factorial-like structure to it. Again, 3 down here, we terminate that 2, we terminate that 1 less than 3, all divided by 3 factorial, and the series goes on forever. And it gives us the infinite series, the Taylor series for this function. And this function does equal its Taylor series. That's just something we'll say, but it doesn't equal it everywhere. We'll talk about that. And I saw a smile. Again, with that, you know, there are theoretical results you can use to demonstrate that a function really does equal its Taylor series most of the time. We just kind of take it on faith in this class that is usually true. I mean, we saw the famous exception that e to the negative something, not famous enough for me to remember it, but it's true in general. However, this does not converge everywhere. And we can use the ratio test to sort that out. A sub k plus 1. I don't want to use factorial notation here because the entire point is that we can't take factorials if m is not a positive integer. but we're going to have the very similar cancellation. M minus, and now we replace K with K plus 1. So we end at M minus K. M minus K minus 1 plus 1. The minus 1 and the plus 1 cancel. And writing K plus 1 factorial is fine, because K is a positive integer. We can just use the factorial notation that we're used to. And A sub K is this. And now we're using the ratio test. I haven't said that explicitly yet, so I'll say it now. That's why we found A sub K plus 1. So A sub K plus 1 over A sub K K factorial over a K plus 1 factorial. That will mostly just cancel out. And then let me see, this thing in the top is going to stay in the top. We're going to have M down to M minus K. Down here, we're going to have that. We're dividing by it, so we're flipping this fraction, and the top becomes the bottom. And you see we haven't wanted to use factorial notation for technical reasons, but we're going to have just the same thing. These things are all in absolute values. The limit as A goes to infinity, and I don't think I definitely made some kind of error here. Because as K is going to infinity, I mean, we should have a whole bunch of cancellation here. And then K factorial over K plus 1 factorial. No, I have not made an error. The ratio test is inconclusive here. Like if we think of k as our variable here, first degree polynomial, this limit exists. What is this limit? Well, the leading term over the leading term. The limit is 1, and that would be failure for the ratio test. And I'm convinced that that should not have happened. So somewhere I made a mistake. And I'm not going to troubleshoot in front of you. You can spend like 10 minutes or half an hour or whatever trying to find that one mistake you did in the second step that caused nothing else to work. It's never very productive. And as a matter of fact, exactly why I'm making the test a take-home test, so that when stuff like that happens to you, you don't have to panic and not have time. So tomorrow I'll either redo that or I won't, depending on my mood. But the correct answer is that the radius of convergence is 1. And usually the radius of convergence makes some kind of geometric sense. So here we're looking at the square root of 1 plus x. And we are centering this at x equals 0. So here's what the graph looks like. Here is 0, here's -1. Of course, to the left of -1, this function is not defined, and it is not possible for the function to equal its Taylor series. So a radius of convergence of 1 gives us convergence on this interval. And this is the largest interval we could have convergence on. If we tried to have convergence on a larger interval, again, we'd have all of these values where the function isn't defined. And it doesn't make sense to say that it equals its Taylor series. And this is actually a general theorem of mathematics, that the radius of convergence is always as big as it's possible for it to be. We don't state that, we don't use that as a tool for finding radii of convergence, because properly speaking, this is actually a statement about the complex plane. And here our intuition about the real numbers matches the mathematics of the complex plane, but that's not always going to be the case. But usually the radius of convergence, if you look at the function, it makes some kind of sense. We saw the exact same thing when we looked at this Taylor series. This Taylor series was centered around 0, and it had a radius of convergence of 1. And again, the radius of convergence of 1 was as big as we could possibly get before we hit 1 divided by 1 and got a division by 0. It's a slight aside. And actually, I was worried that we wouldn't have 2 days worth of material. That's not going to be the case, but the next topic we need to cover is Euler's formula. This is very important that, speaking of complex numbers, it requires us to all be on the same page. So I'll do the calculus and the formula tomorrow, but let me just do the 5 to 10 minute crash course of complex numbers, because I'm never totally clear where this stuff gets taught for the first time. So as children, we're taught that we can't take the square root of a negative number. And then it turns out there are situations where we really need to be able to. And those situations are not, mathematical abstractions. Those situations are things like you're trying to write down the formula for a radio wave. They're extremely grounded situations. And to deal with this, we define I, the very badly named imaginary unit and I has the property that I squared equals -1. And again, there's no help for it now, but calling it imaginary is not very helpful because it gets used, again, in things like modeling radio waves. It gets used in modeling animal populations. It gets used in situations that are clearly not imaginary. And then, once we have this number I, well, we'd like to be able to do number stuff with it. For example, we'd like to be able to do addition with it. And we'd like to be able, maybe before addition, we'd like to be able to multiply it by real numbers. And a real number times an imaginary unit does not simplify in any way. That is to say that 7 times I is 7 times I. There's nothing you can do to make this simpler. And this is perfect. This is actually very analogous. You think of this as the square root of -1. This is actually very analogous to other square roots, right? We might write 4 times the square root of 7, and other than reaching for a calculator and getting a decimal approximation, we can't really simplify this. Similarly, 7 times the square root of -1. We can't simplify that. And because this is formed using the so-called imaginary unit, we call this number imaginary. And then we get to addition. And the imaginary unit acts in a very normal way if we're adding two imaginary numbers. That is to say, exactly as if this were an x or a square root of 2 or anything else. Adding imaginary numbers is easy. You get an imaginary number back again. But when you add a real number to the imaginary numbers, we're back in the situation where this is what it is. This is not 13i, it's not 13 or negative, it's not anything that it seems like it might be. You can just say, well, this is what it is. 7 is 7, -3 is -3. 7 plus 6i is 7 plus 6i. And in general, a number that looks like this is called a complex number. Complex numbers are complete. I don't want to try to turn this into a super formal mathematical statement. But I mean, you think of, you start with the integers and you say, well, or you start with the natural numbers, 1, 2, 3, 4. You teach those to kids. And then it's like, well, we can't do every subtraction. We can't subtract a bigger number from a smaller number. So we get the integers, the negative natural numbers and the positive natural numbers. And now we can add any of those together. But we can't, and we can multiply any of them together, but we can't divide. So we get the rational numbers. We say, well, if we look at the fractions, we can do any division. Well, but then you can't take square roots. So you get the real numbers. But now we still can't take all the square roots, because we can't take the square root of negative real numbers. So we get the complex numbers. And here we're done. There's no like next level, or I guess I should say any next. No, actually, I won't qualify that. I'll just say it. You know, any complex numbers, we can multiply them, divide them, take their square roots, take their exponents, take their logarithms, and we wind back up with a complex number. So that's what I mean when I talk about these being complete. They're complex in multiple ways that we don't need to get into. Multiplying them, for example. We can do it, but it's going to be a hassle now, because to multiply complex numbers, you FOIL them as if you had a factored polynomial. So this 2 times this 6 is 12. This 2 times this -4i is -8i. 3i times 6 is 18i. Then 3i times -4i is -12 times I squared. but I squared is -1. So is this? Yes. So we wind up with this. This -12 and this -1 cancel and give us a +12, which adds to that. There's the 24. Then 18i minus 8i gives us 10i. And we can likewise divide them. Division is more of a hassle, and we don't really need it for calculus. The sort of arithmetic or algebraic operation that I'm really interested in at the moment is exponentiation, e to the a plus bi. And this is super important. I mean, I know it's not always very satisfying just to be told that, but if you're going on to take Math 330 with me, differential equations, where I mentioned, animal populations, this is something we need to be able to analyze for a whole host of applications. And part of it is easy enough to do. I mean, we've got addition in the exponent that breaks the exponential apart. So how do we exponentiate an imaginary number? Well, by using Taylor series, it turns out, and against maybe all expectations, by using the sine and the cosine. You would maybe not think of the exponential as being related to those, but there's a very important formula that relates them. We'll do that tomorrow. We'll also tomorrow, well, always depending on time, but do some integration. Use Taylor series as an integration tool. And if we do succeed in doing all that, we'll have finished chapter 10. I will see all of you then.